Welcome to Introduction to Differential Calculus. Let's start off with the limiting chord process, also known as differentiating from first principles. We could determine the rate of change or the gradient of any function if we graph the function. Let's start off by looking at a graph of y equals x squared. The graph would look something like this. To work out the gradient, we need to pick 2 points. So we're going to pick this point, which we're going to call point A, and it has the coordinates 1 for the x value and 1 for the y value. And we're going to pick another point, which we're going to call point B, and let's pick this as point B. It has the coordinates 2, 4. So the x value is 2 and the y value for point B is 4. Now, if we want to work out the gradient, well, let's call that m. We know the gradient is the difference in y over the difference in x. To work out the difference in y, we take the second y value, take away the first y value, divided by the second x value, take away the first x value. So if we go back to our coordinates a and b, and we're just going to label them, it doesn't matter which way round we get this. So our first coordinate is always going to be x. So we're going to call this coordinate x1, and therefore its corresponding coordinate is y1. This coordinate is going to be x2, and the corresponding coordinate is y2. Now, the gradient would be y2, which is 4, take away y1, which is 1, over x2, which is 2, take away x1, which is 1. Okay, which gives us 3 on 1, which gives us a gradient of 3. Now, if we pick a point that's a bit closer to A, and we're going to call that point C, and it's got the coordinates 1.5, and the y coordinate is actually 2.25, we could work out the gradient between point A and point B using the same method. So the gradient would be 2.25 minus 1 over 1.5, take away 1. Okay, so it's y2 over y1, take x2 over x1. And if we plug that into a calculator, we get a gradient of 2.5. Okay, and we could keep on repeating this process and getting closer and closer to A. Okay, so we're going to choose coordinates that are closer and closer to 1, 1. And if we do that, we will see the gradient tends towards 2. Okay, so we could also do this algebraically using the limiting chord method. Imagine we have a function y equals f of x. The derivative is given by this formula, dy by dx equals the limit as h approaches 0, f of x plus h minus f of x over h. Okay, and we're going to use the function y equals x squared. That basically means f of x equals x squared. So we know this part. Okay, so wherever we see f of x, we're going to add in x squared. We also need to calculate this, f of x plus h. So that means in this function, whenever we see x, we have to add in x plus h. So remember, f of x is x squared, so f of x plus h, wherever we see x, we have to write x plus h. and don't forget the squared outside, so f of x plus h equals brackets x plus h squared. Okay, now we could sub this in our derivative formula. We know dy by dx is, as the limit of h approaches 0, f of x plus h, which in this case is that, minus f of x, which in this case is that, all over h. Okay, now we're going to expand this part out. Okay, and remember it's a quadratic. So we're left with the limit as h approaches 0. We have x plus h minus x squared all over h. Okay, that gives us, so we're going to multiply that by that, that by that, then this by this, and that by that. X squared plus xh plus xh plus h squared minus x squared, because it's minus x squared, all over h. And then we could collect like terms, so we could collect these two. So we're left with the limit as h approaches 0, x squared plus 2xh plus h squared minus x squared all over h. Okay, and then we could simplify further, because that and that cancel, because it's x squared minus x squared. So we're left with the limit as h approaches 0, 2xh plus h squared on h. Okay, and we can actually factorize h out, can't we? Because h is common to the top. So we're left with the limit as h approaches 0. We're going to take out h, so we have 2x plus h on h. And those two cancel. So limit as h approaches 0 is 2x plus h. And as h approaches 0, our gradient, remember this is dy by dx, so instead of h we could put that as 0, we could say dy by dx equals 2x. Okay, and we wanted to know the gradient when x equals 1, so we could substitute the point 1 into this equation, and we're given dy by dx equals 2.